So, looking at the calendar, we've got today's lesson. So click to the lesson starter. And this is the worksheet that we guys have been doing. I'm just going to scroll down and show you that the solutions are just underneath. So have a look at that at your own pace. And make sure we're getting and understanding how to do all these things. Remember, converting a decimal to a percent, we times by 100. Converting a percent to a decimal, we divide by 100. A decimal to a fraction, times by, you need to write it as its place value. So that's 3 is going to be tenths, that 2 is going to be hundredths, that 9 is going to be thousandths. So it's 329 over 1,000. Fraction to a decimal, we just divide the numerator by the denominator. A fraction to a percent, we times by 100. And a percent to a fraction, we divide by 100. Okay. Make sure we're getting the hang of all of them and have a look when you get around to them. Today we are moving on and we're going to irrational numbers. So, irrational numbers are a subset of all real numbers. So when we're talking about irrational numbers, they are a subset of all real numbers. And when I say subset, I mean a part of it, okay? And I'll explain a little bit about that once I write a bit more down. So we're very used to some of the following. So some sets that we are used to, some sets of numbers that we are used to are, there we go. So we'll have, say, counting numbers. Actually, that should be labeled 1, counting numbers. Georgina, what would I mean when I say my counting numbers?
Like 10, 20, 30.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The numbers we're really familiar with, okay? So really it's just every number above from 1. All of our whole numbers above from 1. I just skipped. You can just, it keeps going on and on. Fine. I'll go 1, 2, 3, 4, 5. Just to make Kalia happy. Okay. Another one would be whole numbers. And whole numbers and counting numbers are very similar, but there's one major difference. Negative numbers are not actually whole numbers.
They are negative numbers.
20.
No, whole numbers have 0.
20.
And they have 20 as well, but whole numbers are really, they have 0.
20 is a
Wait,
whole
like
number.
0 at the end of
Yes, 20 is a whole number, Maddie.
Yeah.
How about 40?
Wait, does that count as under this set?
Yeah, 0 and up. Okay, for whole numbers.
Wait, but does it go like 0, 10, 20?
And now we should all know this next one because we did a lesson on it.
Oh, that has
Integers. We have our lesson on integers, and I can go back and I can look up the definition of an integer.
We did this in year 7. Integers.
So if I look back, an integer is a whole number which is either positive or negative. So we now know that all of our integers also take into account negative numbers. So we can say -2, -1, 0, 1, 2, ... And it keeps going on from there. All whole numbers from positive to negative all the way down, yeah.
Everything.
Not everything, just the whole numbers.
No decimal points.
Leo.
Why is it changing colours? Why do you keep on changing colours?
Because they're different sets. That's why they're in different colours.
And also it's easier to see if... Also it's easier to mix it if they're different.
Alright. Now, where do irrational numbers fit in this?
They're not imaginary numbers.
Irrational.
Where do irrational numbers fit with this? Well, first of all, let's explain what rational numbers are before we get into what irrational numbers are. First, let's discuss rational numbers.
What's irrational?
Now, if your parents are ever saying that you're being irrational, it really means that you're just being nonsensical. It means that you're not making sense, you're not presenting a good argument, really. In mathematics, rational has a very different definition. A rational number is a number that can be expressed as a fraction. A rational number can be expressed as a fraction of A over B. Now, when I say A over B, that really just means any two numbers, okay? So it could be 1 over 2. It could be 2 over 3. They're example of rational numbers. Tashara.
Can it be like algebra too? Like x, 1, 3x.
Technically, variables represent numbers, but they are not actually numbers on their own. So if you had x over 3, it could be a rational number if you have a value where you substitute in for x, but x minus 3 on its own is not, because it's not actually any value. Where A and B are integers, sorry. Where A and B are integers, and B is not. Now, you guys may know this, or you may not, so we're going to learn something else if we don't know it. If I have a fraction, what can never be on the denominator?
Decimal.
Not decimal, 0. We can never have 0 in the denominator of a fraction. We can never divide anything by 0. It's something we're not allowed to do. We don't like it. Okay? So you can never have 0 in the denominator.
Have you asked Siri divide by 0? She says I have no cookies and no friends.
Yeah, Cookie Monster has no cookies, so it means he has no friends to share the cookies with, which means he has no friends.
The fact that you remember that is quite worrying.
No, it's Cookie Monster has no cookies and then you're sad because you have no friends.
Let's stop. These fractions are terminating or recurring decimals. So we have rational numbers, right? We have our sets of rational numbers, and they are numbers that can be expressed as a fraction, as A over B. But we want to try and figure out what some examples of rational numbers are. Well, 3, -3, that's a rational number, because we can write it as a fraction, -3 over 1. 2 over 5. Can anyone tell me what 2 over 5 is as a decimal? Bree?
0.4.
Yeah, it's 0.4. So that is a rational number. 0.4, because we can go the other way around. So they're both rational numbers. Perfect squares. So the square root of 9 gets me to 3. So since we can do that to get a number, it is a rational number. Repeating decimals, so 5.27. That is a rational number because we can write that as a fraction.
So would 3 be a rational number because the square root of 9?
Yeah, so 3 as well. Yeah. You could probably have a long list of rational numbers just because it is, the numbers are only two things, either rational or they're irrational in terms of just this sense of rational and irrational. Now, irrational numbers are all numbers which are not rational.
Oh, really, sir?
I know, funny that, isn't it? Irrational numbers just aren't rational. So we just said that a rational number can be expressed as a fraction as a over b. So if we have an irrational number, what do we think that will be? What do we think the definition of an irrational number is? Sean?
E over A.
Not b over a. Leo?
I'm thinking, right, that it's going to be one that, like, goes on, like a number that goes on forever, always changing and not recurring.
Exactly.
Oh, yeah, boys, get straight.
It is a number that will go on forever and ever and ever, not repeating, not terminating, just no pattern. In mathematical terms, we say that an irrational number cannot be expressed as a fraction. So as Leo said, that will result in a decimal that doesn't have a repeating pattern. Okay, so it could be like 0.1246892301449. There's no repeating pattern in there at all. It's just going to go on and on and on. That is an irrational number. The decimal doesn't stop. It doesn't stop. And it doesn't repeat. So if when you convert a fraction to a decimal, and that decimal doesn't stop and doesn't repeat, then that number is irrational. So some common examples of irrational numbers. Sean said a good one earlier, pi. Pi is an irrational number because it goes on and on and on and on and on and cannot be expressed as a fraction. Another one, 5.123031497. I could go on and on and on and on.
Is it possible for us to get one of these in a test?
What do you mean? Like a fraction and express it? Yes, but it will just be, is it rational or is it irrational? Like, that'd be the basis of what you're asking here. And then there's also one more examples of these. And let's say we have the square root of 5.
5.
Oh, here we go.
It leads into a decimal.
It goes into a decimal, but there's no actual answer. So we said that the square root of 9 is a rational number because this here is what we call a perfect square.
That is the imperfect.
And this, yes, imperfect square.
What about 7?
Imperfect square. Yep. 7 would work as well. Anything that's not... So 2 squared is 4. So that's a perfect square. 3 squared is 9. That's a perfect square. 4 squared is 16. That's a perfect square. All the numbers in between aren't because you won't get a whole number for it.
So prime numbers.
Not always prime numbers.
So 2.5 is rational, right?
2.5 is rational because it's a terminating decimal.
But then square root of 5 isn't rational.
Because the square root of 5 isn't 2.5. The square root of 5 is something like 2.2 something, something.
Oh.
All right? The set of real numbers, the set of rational numbers, and the set of irrational numbers make up the set of real numbers. And we have a label for the set of real numbers, and it looks like that. It's like a thick R, but I will always write it like that because you can't really write it any other way. All right? Now, when I say the set of real numbers, it's every number in the world that exists, okay? So all rational numbers and all irrational numbers, if I combine them together, I get all real numbers. For example, if I could talk it as sets and subsets, let's say every student in this class right now, and that's the set of all students I've got. I can split that into two subsets, parts of my bigger set. I can split it into boys and girls, right? And then if I put them all together, then that is the set of real numbers. Leo, I don't need to hear whatever the joke is.
It's not a joke.
Okay, fine. What is it?
Since there's a set of real numbers, is there like a set of fake numbers? Like why does it have to...
Real numbers, and then you guys don't need to know this yet, but there's also a set of imaginary numbers. And that is an actual thing, but you guys don't need to know it. But for future reference, imaginary numbers talks about a complex plane and the argand plane, where the square root of -1 is equal to I. Again, don't need to know that yet.
Is that year 10?
It's year 11 specialist, I think. Maybe year 12.
That's the highest one.
So now we're just going to go through a couple of things where we need to try and distinguish between rational and irrational numbers. So, example, determine if the number is rational / irrational. So I'm just going to write a number, and then we're just going to write I or R. I for irrational, R for rational. Pretty straightforward. So let's say the square root of 79. Is that going to be rational or irrational, Kate? Irrational, because nothing gives us 79 if we square it. So it is irrational. B. 17 over 3. 17 over 3.
Rational?
Rational?
Or irrational?
What does it get me in my calculator, Sean? Because you're going to divide it there.
It's a point.
17 divided by 3.
Yeah, 17 divided by 3. 5, bunch of 6s, 7. So that is actually 5.6. So, if it's a recurring decimal, is that rational or irrational? It's rational.
Oh, I was right.
Dividing by 3 usually gets you a rational number, because I could rewrite this as a mixed number. I could rewrite it as 5 2/3.
Is that why 1/3 is like 3?
Yeah, that's why 1/3 is 3.3333. And so we have a rational number and then another rational number, because 2/3 will always be rational because we're dividing by 3. C. Pi. Pi, rational or irrational? Irrational. We should all know that. Top of our head, pi is irrational. 0.421212121. Irrational or rational?
rational. It's rational.
How many for irrational? How many for rational? It is a repeating decimal. Because we have that repeating pattern of 2, 1. Since it's a repeating decimal, it means that this number is rational. Okay, so we just need to try and distinguish between the two of these now. Any questions? Tashar?
In the test, it would just be pick out which is rational and not.
As far as I'm aware, yeah, that's all we should be.
Test coming up?
No, not till next term.
So will we have to like give an example of irrational?
I'm not sure right now because obviously haven't seen the test, won't write the test, but that would be my guess.
So it's not written yet.
Okay,